Okay, so this is our second video for Unit 3, and we're going to be taking a look at general reactions, but we're also going to be taking a look at molecular reactions versus ionic reactions, as well as net ionic reactions. So to do that, let's start, these are just your general reactions, which were from Unit 2. We're actually going to go ahead and start with the reactions page on page 2 of your notes, looking at molecular versus net ionic. A molecular reaction is everything that you've basically seen so far. So perhaps there was some lithium carbonate and you were able to watch it decompose into lithium oxide and carbon dioxide. A molecular reaction takes that. You'll notice that every single compound is present. And then you'll also be placing your phases next to each of your compounds in order to indicate what they were doing. So were they remaining a solid? Did you actually get a gas that was able to bubble out of the container or leave the container in one way, shape, or form? Those are your molecular reactions. Then you can see the entire thing. When it comes to an ionic reaction, we're now taking anything that was ionic and soluble. So we're joining the concept of your knowing what an ionic compound is, typically a metal ion with a nonmetal anion, and your solubility, which are from the solubility rules. We're joining them together, and you're going to turn anything that looks like that into ions. So you would write them as ions. You would also write them as aqueous. A net ionic reaction means that you'll remove any species, so it could be an ion, it could be water, and you want to remove it because it's actually not doing anything. So it might be like what we saw on the previous video, which was just taking the water molecules out. The water molecules were separate to begin with. They're still separate when they're in solution. They really didn't change. They were liquid to begin with. They were liquid at the end. We wouldn't want to remove something like the iodine that was again in the previous video, where it converted itself from a solid into the aqueous form. Those would be the ones that you would definitely want to keep. So spectator ions are the species that are removed, right? The actual ions that get removed. And they're going to be removed again because all they're doing is sitting around in the reaction. They weren't converted. They started out soluble, they ended up soluble, they didn't do anything, and because of that, they're just spectating the reaction, and so we would take those out. Okay? All right, so we're going to take a look at these reactions down here to give you a nice feel for the difference between a net reaction and your molecular reactions. At this point, you're going to notice that I'm asking you not to balance. I want you to focus on what's occurring as opposed to sitting down and trying to balance everything all at the same time. So we're going to start out, we've got an element, lithium, and we've got water, which is a nice compound. And you'll notice your book does not let you write HOH as the appropriate formula for water, although it's super easy to work with. And the first thing you want to do is you want to decide what kind of reaction this is, and this is going to be a nice single replacement. Because it's single replacement and our lithium could be a positive ion, we're going to be looking for a positive ion to come out of the water. And again, water is molecular, but it is one of the molecular compounds that I had said earlier. Once in a while, they dissociate slightly, and so it's going to turn into ions just a little bit. Lithium is a positive 1 ion, And if you notice, the other side of the water molecule is your hydroxide. Hydroxide is a -1 ion, so the two together are going to make this lovely lithium hydroxide. The hydrogen has to turn into an element, and when hydrogen does turn into an element, it's part of the group of 7 plus 1, and so that is going to be H2 because it's a diatomic element. At that point, you notice that our reactants, I've given you the solid form of lithium, I've given you the liquid form for the water, and now you have to know the forms of the lithium hydroxide and the hydrogen. Hydrogen, you can probably guess, is going to be a gas, and because it's a gas, it's going to actually bubble out of the solution. But the lithium hydroxide, you want to switch over to your solubility table, and you want to be checking for the lithium, and you want to check for the hydroxide. Now, it is really one or the other. You don't actually have to look at all of them. But in this case, lithium falls under the alkali metals that are always soluble. And it says some hydroxides, and really the some hydroxide that we're referring to is the francium hydroxide. Francium being radioactive isn't really going to be insoluble. So you can come down here and under hydroxides it says all alkali ions are also soluble. So when we go back over, we know that what's going to happen is lithium hydroxide is going to be soluble, and not only is it going to be soluble, but it's going to be a strong electrolyte. This that you see right now is your molecular equation. And again, it's your molecular equation because everything is in its compound form or element form. Nothing has been changed into ions. So that is considered molecular. All right, let's turn it into an ionic equation. You're going to take your lithium, and again, it was solid to begin with. We don't want to change that. That was true. You're going to take your water, and that was a liquid to begin with, and again, we don't want to change that. So we're avoiding any conversions of our solids, liquids, and gases. There's your hydrogen. That's gas. Don't change that. What we're then looking for is anything that was aqueous, anything that was actually aqueous. And again, the rules would be it's got to be ionic. With lithium being a metal, it is in fact ionic. And the fact that it was aqueous, it was soluble. So we've met the two criteria that allow you to then separate it into ions. There's your lithium ion, and there's your hydroxide ion. Sorry, not enough room for the aqueous. That becomes your ionic equation. Now, if you notice, there is no change. I'm sorry, let me rephrase that. There's no ion or species that didn't change. Our lithium went from a solid to an aqueous ion. Our hydrogen went from a compound, being part of a compound, into a gas, and our hydroxide was part of a compound and turned into an ion. So nothing is going to be deleted, and since nothing is going to be deleted, this would also be considered our net ionic equation. Okay, let's take a look at another one. Here is aluminum and iron nitrate. And again, this is going to be single replacement. In this case, the aluminum again is a nice metallic element, And because it's a nice metallic element, it's going to swap out the metallic ion that is present. So we're going to end up with some solid iron coming out of the element form. And then over here, we're going to create an aluminum nitrate compound. And we need to know what kind of phase that's going to be. So again, I know it's ionic because aluminum is a metal. I'm going to switch over to my solubility rules in which I see ionic ions. If I scroll down my list of ions that are available, you'll notice that nowhere on here is aluminum. And again, that's okay. What we do have are nitrates. And it says that all nitrates are in fact considered soluble. So since all nitrates are soluble, we know that the aluminum nitrate we were just working with is also going to be soluble. So we can put an aqueous onto that. That is your molecular equation. So again, notice your molecular equations are the equations you've been writing. Now we're going to switch it over to your ionic equation. So the first thing you're going to notice is we have aluminum. Just rewrite that. It's a solid. Do not, again, change solids, liquids, or gases. We have iron nitrate, and we are going to separate that. It is an ionic compound. That's the first part of the criteria. And it's also 100% soluble. That's the aqueous here, so we know that that is going to be written in its ion form. The solid iron, don't change that. Again, no solids, no liquids, no gases. But the aluminum nitrate, again, it's ionic and it's soluble. That's what we're looking for in terms of writing them as ions. Oops, forgot the A. And again, notice I am not worrying right now about how many nitrates are getting written in. I'm not worrying about the balancing. So this is your ionic reaction. As we look at this ionic reaction, what you're now going to notice is that we do have aluminum solid turning into aluminum ions. We've got iron ions turning into iron solid. Then we have nitrate ions, and they are staying nitrate ions. That's what we want to get rid of. That's what's called a spectator ion. It started exactly the same way it ended, and you are looking for exact identical. So because of that, we would rewrite the reaction, and as we rewrite the reaction, we would just omit the nitrate ions, leaving behind just what's actually reacting. And in this case, it would be the iron swapping out the aluminum so that one is an ion and one is a metal. That is considered your net ionic equation. And a net ionic equation is really great when you really just want to focus on what was the change. So when you're sitting in an experiment and you want to just look at how things are going, were you in fact getting, a solid precipitate of iron falling into your beaker? That net ionic equation is really going to tell you. That's also why, if you remember in experiment 3 with the paper chromatography, that I was omitting the nitrates. So I was giving you like iron nitrate, but I dropped the nitrate because the thing of value is going to be the iron ions. All right, let's take a look at another one. This is copper chloride and sodium sulfide, so that is again a double replacement. We're going to take our coppers and we're going to swap them out with the sulfur so that they join up. And our sodiums are going to swap and join up with the chlorides. Again, you're going to notice that the copper is a metal, the sodium is a metal. So both of these are ionic compounds, so we're going to go back over, we're going to take a look at our solubility table and decide whether or not it is soluble. Again, as you scroll on down, copper is nowhere listed, but sulfides are. And as we look under the soluble area, we see that copper is not an option. So copper is falling into this most category of insoluble. That's going to make our copper sulfide insoluble. And that means we're going to have a solid. It's going to actually precipitate. Go back over and we've got our sodium ions. And sodium ions are always soluble. Chloride ions, most of them are soluble, and so that would include our sodium. So we know that sodium chloride is going to be aqueous. Again, that's your molecular equation. Next thing you're going to do is you're going to separate it into your ionic equation. So again, this copper chloride is soluble. And as you get more and more comfortable with these, you can actually leave some of the phases out. And the one that would be most left out is usually the aqueous as you switch it into ionic, because it's understood that if it was in ions, it must be aqueous. For this unit, that's the only time you're going to ever see ions is when they are in fact aqueous. So if you wanted to drop those, you could. Our copper sulfide, however, you cannot separate, and again, that's because it is solid. But your sodium chloride you could separate because it is ionic and it's highly soluble. So this is what I mean here, where you would write your ions without your aqueous. All right, now we would go over and we'd be looking for anything that didn't change. If you notice, the sodium ions did not change. That's a spectator. Who else didn't change? If you said chloride, you are correct. That's also going to be a spectator. So when you write your net ionic equation, you would have your copper, you would have your sulfide, and then you would show it by just showing the copper sulfide, creating a solid precipitate. Again, that makes a nice experimental perspective of what you're looking for, versus above, this molecular equation is much nicer if you're trying to do calculations with stoichiometry, because once you start balancing, it's going to make your life much easier. Okay? All right, as we switch over and we look at our next one, notice what we have here is just a sodium element with a fluorine element. And if you're thinking about what kind of reaction that is, if you said synthesis, you are correct. So with the synthesis, we're going to just take our sodium, we're going to turn it into its ion form, so that's +1. We're going to take our fluorine, we're going to break the bond so that F2 becomes F, and turn it into an ion that's -1. And then notice here, nowhere in here are you told there was water present. So unlike these ones above, if you look, we had aqueous, we had liquid water. That's telling you that you have water. In this case, we would not even go to the solubility table because there is no water. So that solubility table isn't going to be useful to us because no water was present. Even though this is an ionic compound, if there's no water, you can just assume then that it must in fact be solid. So notice that we're not going to have any ions, so writing an ionic equation is not relevant. You can't delete anything because nothing was in ion form and everything has changed over. And so our molecular equation actually turns into our ionic and our net ionic equations. All right, our last one you see, we've got lithium sulfite and we've got perchloric acid. And if your first thought was double replacement, you are incorrect. It is acid sulfite. Notice the sulfite ion right there. So you're going to make some water. You're going to make some sulfur dioxide. And that's a gas, so it's going to actually bubble out of the solution. And then you're going to make some lithium perchlorate. Again, notice a nice ionic compound because we know that the lithium is metallic. We know water is present because of the aqueous symbols, so we're going to jump on over to our solubility rules and take a quick look and notice again, perchlorate says almost every single one is soluble, just that slight change with the potassium ions, but we're not looking at potassium, so we can go ahead and record this as being aqueous. And so highly soluble, a nice strong electrolyte. As we then look and we start switching it over to the ionic equation, again, we're looking for ionic compound that is soluble. Oops, shoot. So there we go. And we have a strong acid, and we're going to need to talk a little bit about acids because if you notice, an acid is molecular. So a molecule should not be dissociating. This one is a strong acid, so I am going to dissociate it, and you'll see a little bit later on during this unit, we'll talk more about how you're going to know. So right now, presume that those are in fact strong electrolytes and therefore strong acids. Again, we're going to have our water as one product. our gas of sulfur dioxide as another product, and then our ionic compound that is highly soluble as our third product. If you can see already, you should be seeing some spectators. Those are our lithium and our perchlorate. And so your overall reaction is going to be hydrogen ions reacting with sulfite ions to make water and sulfur dioxide. One is a liquid, one is a gas. All right, so ladies and gents, hopefully you're feeling pretty good about net ionic equations at this point. And remember to refresh your memories about strong electrolytes being soluble and weak electrolytes being insoluble.